In this video we study directed graphs and networks on them. To explain these things better, I will have to slightly change some events from history. So here it is how it goes. Millions of years ago, there were too many snails in village S. So this is all about snails. We have one village that we will call S, and it has too many snails. And then there is another village, T, that has no snails. And at some point, everybody said, enough is enough, we have to make a plan. And so they made a plan. They wanted to move some snails from S to T. The problem was nobody knew how to do that. And then finally they found one guy who said, you are out of your mind, but my boys can help. We can take a total of 10 snails from the village S to the village A. So that's not exactly the village T, it's not many snails, it's only 10. But those people are flexible, so they can take one snail on Monday and then wait 3 days, then take 2 other snails. So it's just the condition is 10 snails and not a single snail more. And then the person too came up and said that she is an expert in taking snails from A to T. And she can take 80 of them. Not more than 80, but 80 snails. And then good news starts showing up. There was a new person who showed up and who promised to take 20 snails from some other village B to the village A. And then 3 more people showed up. One would take 60 snails from S to C. Another person would take 50 snails from C to B, and another would be capable of taking 20 snails from B to T. And now here is the question. What is the maximal number of snails that can be taken from S to T? Now I suggest you pause this video and give it a try. Try to find some big number of snails that you can take from S to T. But in order to introduce some terminology and some robust algorithms, I will first show you one rather non-impressive number of snails that I will take from S to T. So I will take 7 snails from S to T. So I see you are not going to dance and cheer at my accomplishment, but I have some points to make, so I will show you how to take 7 snails from S to T. And I have one more thing to admit. It's not going to be the smartest nor most elegant way of taking those 7 snails. So I will first take 4 snails from S to C. Then 3 snails from S to A. And then those 4 that went to C will now, those 3 that went to A will go directly to T. 4 snails that went to C will be sent to B. And then now we will split these 4. 2 will go directly to T, and the other 2 will first go to A and then to T. And I want to now show you that this edge from A to T is carrying first 3 snails and then 2, and all we care about is the total number. So I will add these 2 numbers and just write 5, so you will only see the number 5. And now you have seen me succeeding in taking 7 snails. So now here is the notation. These numbers, 60, 50, 20, they are called capacities of edges. And these numbers below the edges, in brackets, are called the flow. Flow in the graph is a function that assigns a value to each edge. S and T are special vertices. S is called source, T is called sink. They are special, and every other vertex has to satisfy some conditions. So here is, let's look at the vertex B. The total flow that comes into B has to be equal to the total flow that goes out of B. So this is called conservation constraint. And of course, the value of the flow over every edge has to be smaller than the capacity of the edge. And so now we define the value of the flow. The value of the flow is, informally speaking, the total number of snails that go from S to T. But now you can pause the video and try to find out the formal definition. What is the value of the flow? And then I will not tell you the formal definition. You have to know it. You should read it from the book. But now, for now, let's keep it as the total number of snails going from S to T. And now we can reformulate our question to what is the maximal value of a flow on this graph. And you may be able to guess 7 is not the maximal number. This was a very small number. So one way to see that 7 is not the best number is to look at something called augmenting path. So let's look at this path on the graph. So we can send more snails just along this path. Each edge on this path, actually every edge on the graph, but now we are concentrating on the edges on this blue path. Every edge has a residual capacity. So that is, the edge can accept more snails. So the residual capacity of the edge from S to C is 56. Then from C to B, 46. From B to A is 18. And from A to T is 75. So this path, this blue augmenting path, can tolerate more snails. So we will now look how many more snails can be sent along this path, and that's the smallest of these numbers, which is called the tolerance of the augmenting path. Now we will send 18 snails will be added to every of those flows. And so this is how we add 18 to these numbers. And now we have produced a new flow that is sending more snails. It's sending 25 snails from S to T. This new flow also is called feasible flow, which means except for source and sink, every other vertex satisfies the conservation constraint. The flow entering the vertex is the same, has the same value as the flow exiting the vertex. Now we have learned that whenever we find an augmenting path, we can improve the flow, we can increase the value of the flow. Now we will find another augmenting path. This flow, even this one that we improved, is kind of a weak flow. There are many augmenting paths, But I want to show you one unusual augmenting path to make another point. So we can send more snails along this unusual path. Why is this path unusual? So let's look at this direction from A to B. The path is S, A, B, T. And this section from A to B goes in the opposite direction of the edge. So you remember from the beginning of the video, one person promised to take snails from B to A. The promised direction was clear, B to A, and the promised number was 20. They promised to take 20 snails from B to A. And in the current flow, we are actually sending 20 snails from B to A, so the edge is at the capacity. But now we can increase the value of the entire flow in the graph by just modifying the values along this blue path. So this augmenting path S, A, B, T can lead to improvement of this value 25. So the edge from S to A can send 7 more snails, and similarly the edge BT can send 18 more snails. But now the question is, how many snails can we send from A to B? And the answer is 20. Why? So when the snails were going along the edges of the graph in the correct direction, we can decrease their number. When 20 snails are traveling along the path, then those numbers, the number of those snails can be decreased by 1, or by 2, or 3, or 17, or actually any number between 0 and 20. So we make the following conclusion. Some edges can have residual capacity in the opposite direction. And now let us find the tolerance of this augmenting path. So the tolerance is the smallest of these green numbers, and it is 7 in this case. We will now send 7 snails from S to T along this path S, A, B, T. So we must now calculate the number that corresponds to the edge from B to A. So not only B to A, so first let's do S to A. So S to A is now 10, but now we do B to A. From B to A, we are now sending 7 snails, but the old number was 20, so now we are sending snails in the opposite direction, so it now becomes as if 13 snails were sent from B to A, because we have to write values of the flow correspond to the snails traveling along the directions of the graph, of the edges. So snails, this number 13 means 13 snails go from B to A. And now the final number is this number of snails from B to T, and that number is equal to 9. Now we have improved the flow, and the value of this flow is 32. And before we move forward, let's summarize what we learned. So I will now list down the words that are new, and you can then rewatch the parts of the video if you want to hear me saying those words again. So here it goes. So we learned about source and sink, capacity of an edge, flow, value of the flow, residual capacity of an edge, augmenting path, and and augmenting path. So now let us go back to the graph and ask again the question, what is the maximal value of the flow? So now maybe it's a good time to pause this video and maybe you can try to find again, can you do more than 32? I just showed you how to send 32 snails from S to T. So now I will count to 3, and while I'm counting, if you press the pause button, I promise I will stop talking, and then you can have some time, some quiet time where you can try to make a bigger flow. So here it goes. 1, 2, 3, done. So this is one flow that has value 50. I'm sending 50 snails from S to T. And I'm kind of curious if any of you managed to send more than 50 snails from S to T. Actually, I'm not curious. I know for a fact that none of you could send more than 50 snails. This is what gives me such a confidence to claim that I found the best possible flow. Here is the original graph. I will first erase these values of the flow to remove any distraction. So I can split. So this is I have one picture that is very, very convincing. I have split the edges in two groups, red and blue. Source is in the red group and sink is in the blue group. And there are 3 edges going between the groups. And the total capacity of these 3 edges is 50. So there is no way you can send more than 50 snails from red set to blue set. And in particular, you cannot send more than 50 snails from S to T. This partition of vertices into 2 sets is called cut. More precisely, it is called source sink cut. And this is not the only cut in the graph. Any partition of vertices in 2 sets is called cut, and every cut has a capacity. So let us look at another cut. So this cut has 2 edges going from red to blue. We have to count only those going from red to blue. These are the 2 edges. And the capacity of this cut is 130. So this cut shows us that it is not possible to send more than 130 snails from S to T. We are actually not learning anything new. This was kind of obvious. We knew that it's not possible to send more than 50 snails. Now this cut shows us it's not possible to send more than 30. We got an obvious, so we are not smarter by realizing this fact. So the maximal value of the flow is equal to the minimal cut. So maximal flow is value of the maximal flow is always less than or equal than the minimal fact, and then the minimal cut. And this we know for a fact. So I'm going to put a box and I'm going to put a check mark in the corner of the box because we know for sure. This is kind of obvious. And now here is the miracle. What we will prove is that the maximal flow is equal to the minimal cut. For now, we are going to put the cloud and the question mark. We still didn't prove that. So this is more difficult thing. Maximal flow is less than or equal than minimal cut. That was obvious. And we will now, the one proof of this fact is by using Ford-Fulkerson algorithm. So I will now describe the algorithm, and this algorithm will find the flow of maximal value and the cut of minimal capacity, and those capacity of that cut will be the same as the value of the flow. So this algorithm consists of several major steps, and every major step has minor steps. So major steps are called explorations of the graph, and every exploration has smaller steps. In each exploration, we start with one flow on the graph. So the input is a flow, and the output is either good news or bad news. So there are one of the two things will happen as an output of the algorithm. The input is the flow on the graph, and the output will be either augmenting path or one very nasty source sink cut. If we get augmenting path as an output, that's kind of good news. Augmenting path means the flow can be improved. If we get source sink cut, that source sink cut will have the capacity equal to the value of the flow, and that would mean the algorithm is over. We cannot improve the flow anymore. And in the beginning, we have a flow of value 0. So let's go back to our original graph. The flow, there are 0 spiders going over each of the edges, and now we can perform one exploration. That first exploration will result in augmenting path, and then we can improve the flow, and then do another exploration, another augmenting path. So to show you the algorithm, I will start from some more complicated flow. I will start from the one we discovered that had value 32. And so now we will explain the algorithm that explores the graph. So in the beginning of this exploration step, the graph is considered unexplored. All vertices except for the source are called unexplored, and they have no labels. And as the algorithm progresses, the vertices will start getting the labels. First, a vertex will be called reached. When we reach a vertex, we will call it reached. And then when we completely study the vertex, finish studying, we will call it searched. In the beginning, everything is unexplored except for the source that is called reached. And so the one step now of this exploration is you take one reached vertex. In this case, you can only take the source. So you start with that vertex and you look at all edges that are going to unexplored territory and that have positive residual flow, residual capacity. So at this moment it's only the edge SC. It has positive residual capacity. It's 38. Then we look at the end point and we labeled it reached. So C is now reached from S. I'm not going to write that reached from S, but actually that should be written there. I want to keep my picture pretty, so I will just put the word reached. Then S is labeled searched. I'm done with S. Now we find another reached vertex, that's C, and we look at all edges that lead into unexplored territory and that have positive residual capacity. We have only one such edge, the other endpoint becomes reached, and C becomes searched. Now we'll move to B, and B is reached from C. We will need that to trace back. So now we have B, B is reached. We look at all edges into unexplored territory. There are two of them, and now their endpoints are now called reached. Once the sink becomes reached, this exploration step is done, and we trace back. We now have obtained one augmenting path. T was reached from B, B was reached from C, C was reached from S, and that is our augmenting path. We now look at what is the tolerance of this path, and the tolerance then is 11, because the edge BT has residual capacity 11, so we can increase the value of the flow along this path by 11, and this is what we get. So the first one exploration step resulted in a better flow. So this we have started with the flow, we got an augmenting path, and the path gave us a better flow. Usually there are several choices that we could make in the order in which explore the vertices. These often result in different augmenting paths, and in the end there could be several possible maximal flows. They will all have the same value, but they may differ in how they are sending the snails along the edges. Now the graph that you see in front of you is very special and very simple at this point. It is so special that now, if all of us perform one exploration step, we will actually end up with exactly the same augmenting path. So I suggest you pause the video. So I will count to 3. During that time you have a chance to pause the video and perform another exploration step. I will not perform it, I will just show you the answer. So counting starts. 1, 2, 3, and now I'm ruining the fun. This is the augmenting path. The tolerance of this path is 7, and once I increase the value by 7 along this path, I get a graph and I get a flow whose value is 50. Now, you do know that 50 is the maximal possible flow on this graph. Nobody could do more than 50. So now I will show to you what is exploration step going to do when the value cannot be increased. So now we will perform the exploration step, and you know the result, you know the end result. We will not find a better flow, so we will not find augmenting path. But let's follow the steps. First we start with the source, and the source is reached. Then we look at all the vertices with positive residual capacity, and that's the only one. Only SC has positive residual capacity, so C is labeled reached, S is labeled searched. Then we study C. From C there is only one edge with positive residual capacity that goes to unexplored territory, that's CB. B is labeled reached, and C is labeled searched. And now we study the vertex B. B does not have any edge that would take us to unexplored territory and that has positive residual capacity. So B is just labeled searched. And now what happens is we have no more vertices that are reached. And that's where the algorithm ends. The vertices that are labeled searched form the red set. Everything else forms the blue set. And the capacity of this cut is 50, is the same as the value of the maximal flaw, and this is the end of the algorithm. So I will now review the terminology, the things that we learned in this video. So we are now getting to an end. So let me first tell you one warning. So this algorithm is perfect, but it's sometimes very slow. This algorithm also would sometimes run forever if we are dealing with irrational numbers. So it's not. So there are some fine print around this algorithm. So, but we are not going to go into details in this first video about Ford-Fulkerson algorithm. So let's just review what we learned. We learned the terminology. We learned what are the capacities of the edges, what is the flaw, value of the flaw, residual capacity, augmenting path, tolerance of the path, source sink cuts, capacity of a cut, and we learned that the value of the maximal flaw is the capacity of the minimal cut, and then we learn the Ford-Fulkerson algorithm. So you should now, I hope now you would be able to read this from the book, to read the formal explanation and the definitions, and it's going to be more clear. So you can then go on the website, so there will be some more notes, some practice problems, and that's it. So this is the end of the video. Thank you for watching.